We've already looked at these three statistics quite a bit. X bar, the sample mean, p hat, the sample proportion, and s squared, the sample variance. We know that when we look at all possible values of each of these statistics, right, with the fixed sample size and independent observations, they each form their own population. And each of those populations has all the properties that a population would typically have. So each of these populations depends on the population that's being sampled from. Right, we've looked at the population of sample means. We know their mean and standard deviation, but we don't yet know the distribution. We've looked at the population of p hats, the sample proportions. We know the mean and standard deviation of p hat, but we don't know the distribution. We've also looked at s squared. Right, we know the sample variances. We know their mean. The standard deviation and variance of s squared, remember, was very complicated, so we're not dealing with that. And we don't know the distribution of the s squareds. Okay, so the distribution for x bar, p hat, and s squared is a description of how those values are laid out, where are they located. And that's what we're going to be investigating in the next couple of episodes. So we know that the mean of the sample means, mu of x bar, is equal to the mean of the population we're sampling from. The standard deviation of x bar, right, is equal to the standard deviation of the population that's being sampled from divided by the square root of the sample size. Okay, so that is, we know where the middle is for the set of all possible x bars. We know how spread out all the x bars are. We just don't know where exactly they're located in between the minimum and maximum values. Okay, and that's the distribution. That's what we want to investigate. So to understand the distribution of the sample means, we have to look to the population that we are sampling from. Okay, so the original population, or the parent population, right, that's what we call the population we're sampling from sometimes. Okay, so the first question we got to ask, is this population that we are collecting our data from normal? Right? Is it normally distributed? Okay, another way of saying the same thing. So, if the population we are sampling from is normal, then it doesn't matter what the sample size is. Right? If the population is normally distributed, then the population of sample means will be normally distributed. Period. End of story. So that's the first thing I check. Okay, so now, reasonable questions. What happens if the parent population is not normal? Okay, so here's where we have to get a little bit more complicated. Not much. We have to check the sample size. Okay, so if the population we're sampling from is not normal, then x bar will not be normal. Okay? But there's something called the central limit theorem that says if the sample size is large enough, right, then the sample mean x bar will behave approximately like a normal distribution. Okay, so in other words, the value of a sample mean, right, the average of small groups when n is small, is unpredictable. But when you get larger and larger samples, the average of those large samples becomes predictable. Okay. Now, if your population is not normal and your sample size is not over 30, then we don't know how x bar is going to behave. And so we don't know the distribution. And so these are our three options. And we're going to run through this list in this order every time. Is the population we're sampling from normally distributed? If so, x bar is normally distributed. If the parent population is not normal, the central limit theorem might bail us out, okay, and give us a sample mean that is at least approximately normally distributed. And for that, we need a large sample size. And typically 30, right, is the cutoff on that. And again, there is nothing magical about the number 30. We'll discuss that more in class. Okay. So if your population is not normal and you have small sample sizes, then we don't know the distribution of x bar. X bar is erratic, and we can't predict how it's going to behave. Now, let's look at some examples. The amount of time it takes a bus running the T Hill route to complete a full loop around campus is normally distributed with a mean of 24.4 minutes and a standard deviation of 3.9 minutes. Okay, so that's information we're being given. We're asked what is the probability that the average amount of time it will take for 18 random round trips to be made. What's the probability that that average will be more than 27 minutes? Okay, so this is the kind of question that's going to make us have to investigate X bar and how is X bar distributed. Okay, so let's take a look at the question itself. Okay. We're asked what is the probability that the average, so right there that's either mu or X bar depending on whether or not that word average refers to a population or sample. So we have to keep reading. So what is the probability that the average amount of time it will take for 18 random round trips? Okay, so 18 round trips of the hill route is a sample, right? The bus runs all day, every day. So there's a lot more than 18 round trips in this population. Okay, so the word average here is X bar. So what this is really asking us is what's the probability that X bar, our sample mean, is going to be more than 27 minutes? Okay, so X bar is my variable. Like we talked about before, we know the average and the standard deviation for X bar, but that's not enough to find probabilities. We need to know the distribution. So if we're going to find this probability, we have to know the sampling distribution of X bar, and that depends on the population that we're sampling from. Okay, so when we look at what we know about the loop times, we know they're normally distributed. Okay, so the population that we are sampling from is normally distributed. We do have a normal parent population. So this is going to inform us about the population of X bars and how X bar is going to be distributed. So we have our checklist of 3 possibilities, and we're just going to run through these 1, 2, 3 in this order every time. So in this case, the population we are sampling from, the loop times, is in fact normally distributed. So X bar will be normally distributed, which means that X bar being normally distributed would allow us to use all of our tools related to the normal distribution, like the normal CDF and inverse norm on the TI calculators, to find the probability or percentiles involving X bar. So if we were to actually do the rest of this problem and find the probability of X bar, which we will coming up very soon, we would just need to employ the tools for finding the probability that any variable that's normally distributed does something. Okay. Now, obviously, since option number 1 is true, X bar is normally distributed because the population being sampled from is normal, that rules out options 2 and 3. They're not the truth. So let's look at some more examples. This time we're going to roll a fair 12-sided die 19 times. And we want to know probably that the average will be between 5 and 7. Okay, so we're rolling the die 19 times, and we want to know the probability that the average of those 19 rolls, so those 19 results will be a sample of what could happen when you roll the die. Okay, so we're talking about, again, the probability that X bar, the sample mean, does something. In this case, the probability the sample mean is between 5 and 7. To find this probability, we would need to find the sampling distribution of X bar. So that would depend on the population we're sampling from. Okay, so when we look at the population we're sampling from, right, it's the outcome when we roll the die each time. So when we roll the die each time, we're going to get one of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So this is a discrete population. So the population we're sampling from, the parent population, is discrete. Normal distributions are continuous. So the population we are sampling from is not normal. Now, what impact does that have on X bar? Again, first thing we want to check in our checklist is the population we're sampling from normally distributed? Because if it was, then X bar would be normally distributed. But in this case, no. Okay. So number 2 on our list. Right? Once we have decided that X bar is not normal because the population was not normal, we got to look at the sample size. So back up here at the top, we rolled the die 19 times. 19, not more than 30. So the central limit theorem is going to say not only is X bar not normally distributed, we don't have a large enough sample to guarantee that it'll be close to being normal. So in this case, X bar cannot be approximated with the normal distribution. So we do not know the distribution of X bar. And so we literally cannot find the probability that the average of our 19 rolls would be between 5 and 7, at least not using these techniques. Okay, so go take an advanced math stat class if you want to go through counting all the options and finding that probability the long way. Okay, so for our next example, it's very similar to the previous one. We're going to roll a 6-sided die this time 200 times, and I want to know probably the average will be less than 3.5. So again, we have a sample of 200 rolls, and we want to know probably that the average, so that word average is going to be read X bar. All right. So shorthand, we're looking for the probability that X bar, the average of the 200 rolls, is less than 3.5. We need to know the distribution of X bar if we were going to answer this question, which means we need to know the population that we're sampling from, which again is discrete. Okay, so that's not normal. So when we go through our checklist to decide what is the distribution of X bar is not normal because the original population, not normal. So in that case, we have to check our sample size. How many times are we rolling the die? This is the average of 200 rolls. 200 is definitely more than 30, so this is not even close. So, yeah, the central limit theorem says X bar will be approximately normal, which obviously rules out option 3. So even though the population we sampled from was not normal, our sample size was big enough that X bar decided to behave in this very predictable, normally distributed way. All right, as every good UT fan knows, the Vols play their home football games at Neyland Stadium. They have since 1921. And in that 100 years, the stadium's been expanded over a dozen times. Each time attendance goes up to meet the new capacity. So attendance figures are going to be multimodal. Right? There's going to be several concentrations. Right? 20 years plus where we had over 100,000 people in the stadium. Right? 5 years where there's only 3,000 people in the stadium. Okay? And so that is definitely not a normal distribution. So we're asked to find the probability that the average attendance for 100 random games is over 50,000. Again, that average is for 100 home games. Okay, there have been way more than 100 games in Neyland Stadium, so this is X bar. To find the probability that X bar is over 50,000, we need to know the distribution of X bar, which depends on the population we are sampling from, which, as I've just discussed, is definitely not normal. Okay. So when we look at our list of options for X bar, the parent population, not normal, therefore X bar is not normal. We have to now look at the sample size to see if the central limit theorem applies. Sample size, we're talking about 100 random home games. That is absolutely more than 30, so the central limit theorem does apply, and X bar is going to be approximately normally distributed. Obviously, that rules out option number 3. Okay, so again, the average for groups of 100 is going to be approximately, not truly, but close enough to normally distributed that we can use all of our normal distribution tools to answer questions about the average attendance for 100 random home games. in this example, we're going to look at how long it takes to get food at the UC. Okay, so we all know that the lines there are not short. Okay, so I'm claiming that wait times are skewed left, meaning most of them are on the longer side, okay, with a few much shorter wait times. Okay. And we want to know the probability that the average wait time for 15 randomly selected patrons is less than 10 minutes. Okay, so again, what is the probability that the average of a sample, 15 randomly selected patrons, so X bar. We want to know the probability that X bar is less than 10. We got to know the distribution of X bar. And that depends on the distribution of the population being sampled from. Population that we're sampling from is skewed left. That is not normal. Okay, so the parent population is not normally distributed. When we look at what might be true of X bar, we can rule out option number 1. X bar is not normal because the wait times themselves were not normal. Okay. Our sample size is 15. That's not a large sample, so we can't use the central limit theorem to say X bar will be approximately normal. So that means X bar is not normal, not even close enough to being normally approximated to use a normal distribution to come up with near answers. So population of X bar here has an unknown distribution, which means we simply could not find the probability of this happening. Just beyond what we know in this class. And for our last example, we're going to think about painting the rock, a long-standing tradition on campus. Okay, so for the purposes of this example, we're going to assume that the number of students who paint the rock each year has a mean of 381 and a standard deviation of 47, and that they're approximately normally distributed. So most years, it's somewhere around 381 students, give or take, about 47 a year. Okay, and getting way higher or way lower than 381 becomes less and less likely. All right. And we're going to randomly pick 5 years, and I want to know what is probably the average number of people that painted the rock in those 5 years is somewhere between 375 and 400 people. Okay, so what tells me this is all about X bar? Again, 5 years are randomly selected, and we want to know about the average. Those 5 years are a sample. The rock has been painted way more than 5 years. And so the average we're talking about here is X bar, not mu. And so we want to know probably that X bar is between 375 and 400. To do that, we need to know the distribution of X bar. As always, that starts with the distribution of the individual values that make up our sample. So the individual years. Okay, so we know that the number of people who paint the rock each year is approximately normally distributed. All right, so if the population that we are sampling from is normally distributed, what does that mean for X bar? X bar is going to be normally distributed. All right, so some of our sample means will be less than 381, some higher than 381, and they'll be symmetrically distributed about that average of 381. That's what that's saying. All right, so X bar is normally distributed, which of course rules out the last two options. Every time I go through and try and determine what is the distribution of the sample mean, I'm going to go through this checklist. Is the population we're sampling from normal? If not, is the sample size large? And failing both of those, we got nothing we can do. So that covers the distribution of the sample mean. Right? We need to check to see if the parent population is normally distributed. If not, is the sample size large enough? All right, there's your checklist. Good luck. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols.